Welcome to the place where we gain knowledge through the lens of creativity. I am Aaron Dworkin, and this is Artful Science. Thanks again for joining me here on Artful Science. Today's show is AstroCappella, Exoplanets and the Music of Science. Very interesting show. And my guest is Patricia, otherwise known as Patty Boyd, who is Chief of Exoplanets and Stellar Astrophysics Laboratory and Project Scientist for the Transiting Exoplanets Survey Satellite at NASA's Goddard Space Flight Center. Patty, welcome to the show.
Thank you, Aaron. Thank you so much for having me.
For sure. So, I'm so excited to talk about this. As you know, we are here at the intersection of arts and sciences. You had this amazing scientific career while also engaging in music and the arts. So I kind of want to touch on two main topics in our short time. So first, let's just delve into exoplanets. A lot of people may not even know what exactly they are. So what are they? How many are there out there?
That's a great question, and it's a really exciting field. So I'm really delighted to talk about exoplanets. So the Earth is a planet in our solar system, and we are orbiting around the sun. The Earth goes around the sun one time per year, and there are 8 planets total in our solar system. Exoplanets are planets that orbit stars other than the sun. So stars that you see up in the sky at night are basically the same thing as our sun. They have different sizes, different ages, different temperatures, but the sun is one of hundreds of billions of stars in our galaxy. And exoplanets are planets that orbit stars other than the sun.
Awesome, awesome. And so, having grown up loving Star Trek and, Star Wars and all of these things, one of the things that's interesting is that separate from the science fiction that I recall from my childhood, I don't recall there ever being commentary. And I almost think that if I would have said, even to a teacher, well, there's a lot of other planets out there, I feel like they would have been like, what are you talking about? Is this relatively recent, the actual kind of factual knowledge and understanding that exoplanets exist? What kind of time
Yes.
come to know this? Yeah.
Yes, your recollection of your childhood is absolutely accurate, and it's the same as mine. And so, we've been looking at things out there in space using telescopes for over 400 years. Galileo started that 400 years ago. So there have been scientists that are looking to understand how the universe works, but the question of whether we would ever be able to actually see something as small as a planet with any technology that was at our disposal was basically considered almost like a non-answerable question for a long, long time. So while, folks who wrote science fiction and even scientists themselves dreamed of the possibility that there could be planets around other stars, just like there are planets around our star, the sun, that answer was really out of reach until very, very recently. So it was in the 1990s when the technology and the techniques and everything came together, detectors, computers, methods, sizes of telescopes, the capabilities of instruments came together where we start to really observe the signs of planets around other stars and, measure their orbits, measure their masses, and confirm that they were actually there. And it was like, I would say, several years where it was a big debate, like, are we seeing actually an exoplanet with this data or something fooling us? But they did become confirmed in the 90s. And since then, it has absolutely exploded. So we now know of over 4,000 confirmed planets around other stars. We've got several thousand more candidate exoplanets, so ones that are waiting to be confirmed. And if we can extrapolate what we've learned so far, where do we see these planets around other stars, and how do we extrapolate that to understand how many planets are in our galaxy alone? We now believe that there are more planets than stars in our galaxy, and we have a very firm foundation for believing that.
Wow. And so, I mean, it's truly amazing. And so kind of delving into this more, and of course, this is, my, layperson's primarily artistic brain coming at it. I think about when we look up at the sky and we see things, easy to see stars, they're emitting light and all of that, and so many other things. And obviously planets aren't emitting light. So I'd love to just get a little bit more down into of how do we actually have the ability to see little planets out there with the power of telescopes, or are we discerning their existence in a different way?
So there are actually a variety of methods of discovering and studying exoplanets. And as our technologies get better in certain areas, we find more planets using those methods. So while there are some solar systems out there, extrasolar systems, where the planets are big enough and young enough and hot enough and illuminated by both their star that they're around and the fact that they're still giving off some energy, we can see some of those planets directly. We call that direct imaging with specific techniques, specific observatories, and it's a very small number of systems, but they're out there and they look amazing. We have enough data on them that you can actually see these planets moving, over the years. But the vast majority of the planets that we've discovered to date have been found by something called the transit method. And so that's very similar to like an eclipse. So lots of people have seen lunar eclipses. Many people in the US were lucky enough to see the solar eclipse a few years back. There's another one coming up. So that's when you have an object that's passing in front of the star, it blocks some of the light. And so in our case, when there's an eclipse, the moon passes in front of the sun. It blocks basically the entire disk of the sun. A transit is very similar to that. If we are looking at a system in just the right orientation so that those planets are orbiting the star and they'll pass right in front of that star with respect to us, there's a tiny little dip in the light when the planet goes in front. That's called a transit. And that is something that you can see in the light curve, like how the light changes in a star. The Kepler mission was launched about 10 years ago to do what we call transit photometry. So it did this photometry measuring the light on an ensemble of stars, 150,000 stars, looking at them all at the same time without blinking for years, looking for these tiny dips when the planet would pass in front of the star. So that's how the majority of the planets that we're studying today have been discovered. But there's also another method called the radial velocity method. So if the planet doesn't pass in front of the star, but it still moves the star around because of its gravity, they're each orbiting the common center of mass. It's not actually that this star is fixed and the planet is moving around it. And that motion that's induced on the star causes it to wobble in space. And we know that all things that are like coming towards us will have what we call a blue shift in the light. The spectrum of the light will look a little bit bluer, and if it's moving away from us, a little bit redder. And so we call that the radial velocity method, measuring those changes in the velocity. For a long time, that was one of the best ways to detect planets around other stars. But it really preferentially picks out the planets that are massive, right? So that they have a lot of mass, the signal is large, and if they're going around quickly, we have a chance of measuring that variability over and over again. So that selected a certain type of planet that we would see. Now, the transit method is selecting different types of planets. I think one of the most exciting things that we found about these thousands of planets out there, when you look at our own solar system, we have two types of planets. We have the little rocky planets. Earth is one of those little rocky planets. So is Mars and even Venus, believe it or not, and Mercury. And then we have the gas giants, right? So there's Jupiter's the big one, big on the block, but there's also Saturn, Uranus, Neptune. They're gaseous. They've got huge atmospheres. And there's not anything in between something the size of Earth and the size of Neptune in our own solar system. But when we look at these planets that are discovered primarily by the transit method now, what we see in the statistics of the sizes of planets that we find is that the most common planet out there in the galaxy is larger than Earth, but smaller than Neptune. That peak in the distribution is right there, something that we don't have in our solar system. So that's just a really interesting fact.
Fascinating, absolutely fascinating. And you had mentioned too that we're kind of that, we've discovered, I think, over 4,000, but we're still, there's many thousands that are kind of, we're waiting to confirm. Is part of that confirmation that when we see this data like a shift, or we see that there's been a light change because there might have been a transit, do we kind of wait to see if that happens in regular intervals of time that can then be predicted, and so then we know that it's an orbit? I was just kind of curious when you said we kind of, it's confirmation, or is that just that additional scientists need to look at the information and kind of confirm themselves before we consider a planet to be confirmed?
So planets that are discovered by the transit method, candidate planets, are they become candidates based on one type of data, the light curve, right? So we see these tiny dips, and you're absolutely right. Like, we see one dip, that's exciting, but we have to see two dips in order to measure the period. And we usually wait until we see three dips to make sure the period, the time between dip 1 and 2 is basically identical to the time between 2 and 3. And so we can get the period out, and depending on how much light is blocked, we can also get the size of the planet relative to the size of the star, and how much light is blocked. But that's still just one type of data. And there are some things that could fool us. So usually when we're doing all this photometry of many stars at once, we're looking at just the light that's in a tiny little piece of our detector. And you can imagine that either the star is all by itself and the planet is just going around the star, or there could be something else in that little piece of the detector, like say a star in the front, but what would be like a background star, a star that's in the background. If that star is an eclipsing binary, and we know that, half the stars in our galaxy are in binary star systems, some of them eclipse. So if we had an eclipsing binary in the background and a bright star in the foreground, that little eclipse could look like a transit. So one of the things that astronomers have to do is to follow up these interesting photometric signals to see, is there any indication of a background eclipsing binary there? And there are just other ways of, basically looking at your data and making sure that what looks like a candidate is completely consistent with that being a planet passing in front of the star and not something else that could fool us.
Gotcha. Absolutely phenomenal, amazing. I've learned so much more about exoplanets than I ever do previously. So I want to switch gears as we run short on time. Usually I end asking my guests if they have a musical interest or a practice that they do. You have a lifelong history in music and in the arts, and not only that, but tying it to science. So just wondering if you can share with our guests and our audience, rather, a little bit about the chromatics and especially your project, AstroCappella.
Sure. So the Chromatics is a 6-voice a cappella ensemble. There's 3 men and 3 women. And we met through our connections to NASA and space. So 4 of us work at NASA. 1 of us is an APL engineer. He does space battery work. And the 6th person is a music and math teacher. So she's an educator. And we started singing a cappella together. Loved it. We love singing a cappella. It's close harmony. It's really awesome. We were all very musical. We were also very sciencey. And we decided to write a grant proposal to mix to put a blend our love of singing, love of a cappella, and our love of science. We're all like very passionate about both. To write our own songs that would bring the universe, like what we know about the universe and how we know it, like so that the facts and what's out there as far as what we're measuring and how we're measuring them, bring these to audiences through songs. So our main target audiences are students. We have some songs for elementary students and middle school and high school, but we're also really also focus on like informal education. So museums, science centers, that type of thing. And each one of our songs has a lesson plan, an activity, background information. Many of them have videos. And we're just very energized to share our love of science with a large audience, especially through music. Because one of the coolest things about lyrics in particular is that when you learn the lyrics to a song, it actually gets like embedded in your brain. We can remember all the songs from Schoolhouse Rock, what are the ingredients in a Big Mac, or because we learned it in the song, in the commercial. And so our idea was like, let's get some really interesting science facts into these songs so that students can remember something about like the electromagnetic spectrum, or, you know, how big is the moon, or how far away is Mars. And we've had a really good time, you know, presenting these songs to a variety of audiences through the years.
It's just extraordinary. I was actually thinking you were about to break into song there for a moment too. So it's, it really is. And I think you really hit, you know, that such important point that the arts could be this medium through which that understanding and medium, and I would probably add the connection, right? That passion that you have for exoplanets, when you share that through song, I think that especially young people, they are able to engage in that passion and share in it, in addition to the knowledge and information that you're conveying too. It's truly just amazing, amazing work that you are doing. Patty Boyd, thank you for helping us gain knowledge through the lens of creativity here on Artful Science.
It was my pleasure, Aaron. It was great to talk to you. Thanks for having me.